So an argand diagram. What is an argand diagram? It's a geometric plot. So it's some kind of plot that we have. Let's put an axis over here. Geometric plot of complex numbers, right? So we get complex numbers. And what's a complex number? We're saying that it's a number, for example, such as z equals x plus I y. And we have our x-axis, which takes on the form of a real part, which we call, let's say, RE. And RE of z is basically that part. Because it's a real number, it's not something that actually has a value. And then we've got the imaginary part on the side here, the imaginary part of z, which is going to be that value on the side over here. And that's the imaginary part. So we've got an imaginary axis and we've got a real axis. And this is known as the complex plane. Right? This is known as a complex plane. So if we had to, for example, plot some kind of value on here, like let's suppose I want to plot -3 plus 2i. And let's say z is given as this. Then in this case here, the real part will be -3 and the imaginary part will be 2. And so that would be where we would plot that from there. And as we change this around, we can make this into negatives, we can make this into positives, and likewise, it works very similarly in this fashion to a Cartesian plane, but we just have this I. And what is I? I is the square root of -1. So the concept of an imaginary number is built on the idea, they're actually calling it imaginary for a reason, is the fact that it's a number whose we actually saying that if we have I squared, it'll equal to -1. So an imaginary number is a number that when you square it, it becomes a negative number. And imaginary numbers are always defined with some kind of square root of a negative number. And so you can replace it with all kinds of forms or different parts of I. And if I have I cubed, for example, that'll become that cubed. So it will be -1 square root times -1 square root times -1 square root. And that'll become -1 square root of -1. And then you can see that that is actually I. So that's going to be -I. And if we look at another part, another example of imaginary numbers, if I've got the square root of -16, for example, I can actually find this using an imaginary number. So if I is equal to the square root of -1, then the square root of -16 is equal to the square root of 16 times the square root of -1, which will equal the square root of 16i, which will get me 4i. And what actually is 4i? 4i is actually going to be over here. That's 3. So this would be 4 over here. And it would be that part of the y-axis, the imaginary part of the y-axis over there. Okay. So we can also just connect the line even. Let's say we connect the line from the center. There we can see that that would represent the hypotenuse of this. And so when we find the hypotenuse of this, we realize that we can have some kind of angle that can exist on either side. And so when we find the modulus, right, of z, we actually finding. So what is the modulus of a function? The modulus of the function is actually the It's like the magnitude of a complex number. Let's look at it separately. If we look at, for example, let's say I want to find the modulus now separately of z, which is equal to a plus ib. We can write it in short as mod z equals the root of z, which is equal to the square root of the real component of z squared plus the imaginary component of z squared, which is basically a squared plus b squared, because that's the real component, that's the imaginary component from there. And once we get the modulus of z, we obviously have to square root that. We have the magnitude of that particular vector, which then takes us on to the argument. And the argument of z is given by, let's say, it's given by arg z or arg z, which is shift 10, and we always use y over x. So I can see that my y value here is always going to be b, because 10 is always y over x over a. Now, shift 10 is arc 10 on a calculator. We can use radians as well. In this particular coordinate over here, we got -3, and it's actually 2i up. We could write it like that. Or we could write the vector out completely as z equal to -3 plus 2i. And so if I have to find the modulus of z for this, it's going to be -3 all squared plus 2 all squared square rooted, like that. And that's going to get me 9 plus 4, which is the square root of 13. And so the modulus of z will be the square root of 13, which would be the magnitude of this line from there all the way till there. If we give it some kind of direction, we can then deem it a vector, because vector has both magnitude and direction as well. So keeping that in mind, we can now calculate this angle over here, which we generally need. If I have to make this into a triangle, I could extract y over x. And if I have y over x, like that, so that's my y value, that's my x, and that's alpha. And if I take tan of alpha, it'll equal y over x. And so the angle alpha is equal to shift tan y over x. But I can see that my y value is my value over here, which is going to be 2. That's going to go in place of y, and that's going to go in place of x. And so if I have to calculate that part there, possibly taking the positive of 3. Either way, if I take 2 shift 10 on a calculator, 2 divided by -3, so grab a calculator and shift 10 of 2 divided by -3. And we make the -3 into a +3, we'll get 33.7 degrees for this, right? We'll get alpha is equal to 33.7 degrees as positive. It will be a negative, which implies it's on the other side. So this would be -33.7 because it's on the left-hand side of the vector. But automatically, if you take the absolute value of that, this number over here is going to be 33.7. So automatically, this is going to be 180 minus 33.7 degrees. So 180 minus 33.7 will come to 146.3 degrees on that side over there. Okay, so From this, I've calculated the angle, which is the argument. So this whole part of here, what I've done now is calculated the argument. And in this case, it's going to be alpha. That would be the argument, right? So the argument is not alpha, sorry, theta. So that's going to be the argument of the vector, because 0 degrees begins over here and goes in an anti-clockwise direction all the way back. So the angle that this would be making would not be 33.7, it would be 146.3 for this particular part here. Okay. So in an argand diagram, let's quickly get a quick sketch of an argand diagram. It says point A and B are represented by the complex numbers -3 plus 2i. Okay. So A is faced with the equation -3 plus 2i, and B is faced with the equation 5 minus 4i, respectively. The points A and B are the endpoints of the diameter of a circle. Points A and B are the endpoints of the diameter. So let's plot this out, right? So we got our imaginary component of the year, we got our real component of the year, and we can see our real -3 left and 2 up. So 1, 2, 3, and 1, 2 up there. And on this side here, I got 5 to the right and 4 down. 1, 2, 3, 4, 5, and 1, 2, 3, 4 down. 5 to the right and 4 down. And this is going to be the point A. This is the point B. And it says the points A and B are endpoints of the diameter of some kind of circle. So that means if I connect these two, I can actually draw some kind of circle around it. And so I can be faced with something that looks like that. Okay. Now, if you want to find the equation of C, it says the points B are endpoints of diameter of a circle C. So that means the center of the circle is somewhere over here, right? So it could be like somewhere here, let's say. And if I get it in this equation form, how am I going to find this? So the first thing I need to understand is, okay, well, for every circle we have some kind of radius. So how would I find this radius? How would I find this length over here? How would I find that length over there? Would it be possible? I have the coordinates over here, which is going to be -3 and 2. And I have the coordinates over here, which is given as 5 and -4. So with that, I can use a distance formula. And if I find the distance, so if I find the length of AB, it's going to be equal to the square root of -4 minus 2 squared plus 5 minus -3 squared. And so that's equal to the square root of -6 squared, which is going to be 36. And 5 minus -3 is 8 squared, which will be 64. And so that'll add up to 100. And so that will become 10. So the length of AB would be 10. And so therefore, we know that the radius is going to equal 5. Okay, so now we got our radius is equal to 5. The next thing we need to do is find the center of the circle. Now to find the center of the circle, we can use the midpoint formula. And so when we find the midpoint of AB, it will be x1 plus x2 divided by 2, y1 plus y2 divided by 2. And so that will become -3 plus 5, which should be divided by 2, and 2 minus 4 divided by 2. -3 plus 5 will be 2. 2 divided by 2 is 1. 2 minus 4 is -2. -2 divided by 2 is -1. So that's going to be the center, which will be 1 to the right and -1 down. and that's where the center C would lie. So if the center C would lie there, then what we have to now do, it says find the equation of that in this form over here. Now, firstly, this is the modulus of z minus a, where a is a complex number. Over here, you can see it says there, a is a complex number. So that means that a will be represented by x plus ib. And on that same note, we can see that b is also a real number. And this over here, z minus this, is basically going to be quantified, or the magnitude of this must come to b. We're looking at the center, we know that the radius is equal to 5. That is actually what b would be. So b would take on the value of the radius, which is 5. And a would take on the value of the center, in which case, built on the concept of the center, my x value is 1, my b is -1, so a will equal 1 minus I. And so therefore, we would put them together, and our final answer would look like this. We would have the modulus of z minus x plus ib, which you can write as 1 minus I, is equal to 5. All right, and that would be the equation that we're looking for that. So for this question over here, what we have is, particularly, it says the circle D with the equation z. So let's write down this equation over here. This equation says, we've got it in modulus argand. So remember that z, if I take a negative out and put the rest in a bracket, it's going to be plus 3i, like that. And that will equal to 2. And we must remember that that 2 over there is going to be the radius of my circle, and that is going to give me my center of my circle. All right. So from this here, I can see the center is going to be at 2 and 3, and it's going to be the radius of the circle. And it intersects C at the points representing complex numbers z1 and z2. All right. So it intersects C at the points representing complex numbers z1 and z2. So let's see if we can firstly put this in some kind of diagram. Okay, so we've got some kind of diagram. And what we have here is we're going 2 to the right, and we're going 3 units up. So 1, 2 to the right, and 1, 2, 3 units up. And we know that's going to be the center over there. And we know that this circle will have a radius of 2, which means that it most likely will go as high as 5. It'll look maybe something like that. And it will go as high as 5 goes, so it'll go slightly left there, and it'll go down till 1, and as high as 5, and it will go to 4 on the side over here. So because it's a radius, right? So 3 plus 2 would get me to 5 over there at the top, and on the side here would be 4, just so we could get those coordinates on that side there. This is going to be my imaginary component. This is my real component over here. Now that we have that, it intersects C at the points representing the complex numbers z1 and z2. Okay, so now from the previous part, the previous C that we had, all right, so C basically, we had the equation where the center was equal to 1 and -1, and the radius was equal to 5. And so that equation there was somewhere at the bottom here, at the radius of 5. Okay, so it intersects C at 2 points. let's draw that quickly. So we've got 1, negative 1, which would be over here. And we've got some kind of, let's have a radius of 5. So 1 plus 4 will equal 5 to the right. And it'll go 4 up till there. And 1 minus 5 will be negative 4. So it'll go up to negative 4. It'll go down from negative 1 minus 5 to negative 6, which will be the lowest point of that particular. But anyway, just to sort of get that gist of it, these two are intersecting at 2 points. And it says these 2 points carry the complex numbers z1 and z2. So that's going to be over here and over here. Either one, either way, basically. Now from here, what we need to do is realize that we're actually solving this simultaneously. And we have 2 circle equations over here. And the circle equation over here at the top is going to be x minus the center. Now the center here was 2, 3. And this center over here is 1, negative 1. And so this is going to be faced with the equation x minus 2 squared plus y minus 3 squared. And that's equal to the radius, which is equal to 2. And over here, this equation is going to be x minus 1 squared plus y minus 1 becomes plus 1 squared equals a radius of 5. And these two we need to solve somehow simultaneously. So how do we do that? We have to bring it together, and we have to do a bit of calculations with that. Now, if I have to maybe multiply out the first brackets, I'm going to end up with x squared minus 4x plus 4, all right, and plus y squared minus 6y plus 9 equals to 2. All right, let's just double check that. So the radius had to be squared. So that is actually not equal to 2. It's equal to 2 squared, which is equal to 4. Okay, so let's just make that into 4. And let's just remember that is squared. Pythagoras theorem built on the concept of it. Squared plus squared equals squared. So that's going to be squared. Okay. So now that I have that, that's going to be my first equation. Let's call it equation number 1. And let's call this one equation number 2. I can simplify this. 4 and 4 will cancel out. And I'll be left with x squared minus 4x plus y squared minus 6y plus 9 equals to 0. And now let's get the second equation. The second equation coming from here, it'll be x squared minus 2x plus 1 plus y squared plus 2y plus 1 equals to 5. And so this comes to x squared minus 2x plus y squared plus 2y. And the 1's plus 1 is 2, minus 5 becomes negative 3 for this one over here, equals to 0. And now we have these two, which both equal to 0. So maybe I can equate them, or maybe not. Maybe I can eliminate something and get an equation. If I put them below each other and subtract each other, so let's say I put equation number 1 over here, so this is equation number 1, and I put equation number 2 over here, then this will become x squared minus 2x plus y squared plus 2y minus 3 equals 0. And so x squared plus x squared cancels out. Negative 4 minus becomes plus, so negative 2x. Y squared cancels out. 6 minus 2 is minus 8y. And 9 minus 3 is going to be plus 12. Plus 12. All right, let's double check. That's all good. And that's going to equal 0 over there. Okay, did I do this perfectly correct? So I have to make sure I expanded that correctly. And I expanded that one correctly. And I got 4 canceling out with 4, so I'm left with 9. And then on this side here, I got x squared minus 2x plus 1. And I got y squared plus 2y minus 1. I got 1 plus 1 is 2, so I ended up with negative 3. That looks good as well, but I didn't square this part here. So this is supposed to be 25. So this will be 25. That makes more sense now. And 2 minus 25 is going to be negative 23. And a negative 23 is what we're supposed to have over here. And then 9 plus 23 is going to come to 7 and 2, so 32. So that should be 32. All right, if I bring this over to the other side, I got 32 equals to 2x plus 8y, and that's equation number 3. All right, now from this here, I can rearrange this equation. I'm just basically solving simultaneously. I can substitute equation 3 into either 1, or I can substitute it into 2, and then solve for y or solve for x, depending on whichever one I want. So I'm going to simplify. I can see this can divide by 2 all the way across. So I know 16 will equal x plus 4y. And so therefore, x can equal 16 minus 4y. And now that I have that in that form, which is x, I can substitute it back into one of the forms which I need to replace y with, or replace x with y. Okay, so let's suppose I substitute it into the more simpler of the two equations, preferably this one over here. I'm going to substitute it into equation 1, and I'm going to get 16 minus 4y squared minus 4 times 16 minus 4y plus y squared minus 6y plus 9 equals 0. So that's going to be 256 minus 4 times 6 is 64. So 128y plus 16y minus 64 plus 16y plus y squared minus 6y plus 9 equals 0. And so 256 minusing 64 plus 9. Let's grab a calculator from here. And let's see if I can get that in order there. All right, and it's going to be 256, quite a long story from here. 256 minus 64 is equal to 192, and 192 plus 9 comes to 201. So this will come to 201 plus, so minus 18, minus 118 y plus 201 for that in total. And that's going to become, okay, so got the y values in there. And then I got y squared, and I'm missing another y squared over here. There's supposed to be y squared there, 17y squared. Okay, equals to 0, and then we can try and solve that as well. Okay, getting it into the next part over there. After doing all of that, we end up factorizing that into those two parts over there, getting my x values over there, and getting my y values over there as well from there. Okay. And once I've got that, I can then rewrite it in this form, because I got my x and I got my y, so I can put it back into the original form there.